Hi everyone, my name's Joe, and you might be able to tell that I'm not actually from Denmark originally, but I've been a postdoc with Bjørkhammer in Aarhus for nearly 2 years now. And in my time here, I've been working on the augmentation and application of universal potentials in material science, particularly for structure prediction. I really don't need this slide. I think this audience is well equipped enough to know the challenges that face atomistic simulations and the systemic need to make these higher accuracy methods, DFT, but also things like coupled cluster, cheaper. And machine learning is certainly the avenue that we have recently taken to trying to tackle this problem and make accessible some problems, be they complex molecules or large-scale surfaces or interfaces that my colleague Ned will speak to you about later in the week. Certainly, these problems require solutions outside of what DFT has to offer. And I don't really need to talk to you about neural network architectures either, or the fact that in the past, however many years now, they have begun to become so much more prevalent in society itself, with not just in our field. But I think the most significant thing is that now data is becoming so readily available with millions and millions and millions of DFT level calculations, millions of structures being available to us. And when we combine this level of data with things like neural networks, we actually gain access to this new concept, or relatively new at least, is that one might have something called a foundation model, a model which, at least in essence, is attempting to be able to solve many, many different systems with different stoichiometries and different geometries. It's able to model all of these things in one easy-to-access potential. And just to kind of highlight how important and quickly developing this part of the field is, all of these potentials from the MapBench discovery benchmark that I've just highlighted were all produced in March this year. So it's really a field which is seeing some really rapid development. And for good reason. Let's take one potential, CHGNet, which was new when I made some of this work, but is certainly by no means new or the best in terms of metrics now. And the extrapolation that these potentials can have from data that isn't even part of the training data set can be quite remarkable. So we look at the example of these olivine clusters, magnesium, silicon, oxygen clusters, which astrochemically perhaps relevant. And we can see that CHGNet actually already knows what the correct structure of this is according to DFT. And the same thing's true for this silver oxide surface reconstruction. It knows what the structure is. The same thing true for this copper oxide surface reconstruction. So there's certainly some extrapolation to be gained. There's certainly some benefit to having trained these potentials. But there are certainly also some caveats. There are different surface reconstructions here, which for silver oxide are all incorrect when you query this potential, and a different magnesium, silicon, oxygen, pyroxene cluster, which is also incorrect, not just in CHGNet, but in other potentials as well, call them 7net and MACE, but in many others also incorrect. And the same can be said for some of these surface reconstructions here. So it's not just a facet of one potential being perhaps a little confused, but in fact that there's a systemic tendency for certain potentials to make mistakes when extrapolating. So clearly, we need some way of combining these two things together. Both the idea that universal potentials already have quite a good extrapolative knowledge of space, but that we might need to correct them in a small amount in some region when we're exploring. So we need some way of exploring and some way of correcting these universal potentials. And I'm not going to go too much into how we generate structures. People know about global optimization and all the different methods that one could use to search for structures. If we're interested in having that discussion, then that's what the coffee break's for and all of these other discussions. So please, let's talk about that. But for now, let's talk about the idea that one needs some kind of active learning method, exploring the landscape, doing DFT, improving your potential in some way, and then iteratively repeating this process until you have something really useful for your specific application. And I think the first thing that will jump to people's minds will be fine-tuning. You take your network, which is already, in the example of CHGNet, 400,000 parameters trained on 1.5 million structures, but this could be any network architecture with however many parameters, however many training data, it doesn't really matter. You could take that and then you find some new data and you just train all of those parameters on that new data. It's possible to do. You might get some good results from it, but it also opens you up to the dangerous possibility that you forget some stuff. Catastrophic forgetting, I think they call it. So this is perhaps isn't exactly fantastic, and there is an alternative, which is some form of delta model. So you take your universal potential that you begin with, and instead you use some model. In this case, we've used the Gaussian process regression, but one could train a delta network or any other number of ways of fitting this difference and actually learn the difference in energy between DFT and your universal potential, and consider the combination of this delta model and the universal potential to be your new surrogate potential. And just to compare between these two ideas that one might either fine-tune or delta learn to solve a problem like this cluster that I showed to you earlier, where each of the different colors represents one of the structures and the line represents the relative energy in the model for a different amount of data. One can see that the amount of data that's required in a delta model to correct the behavior of this combined potential when you're using a delta learning strategy is much, much lower than when you use fine-tuning. But certainly in the high data regime, fine-tuning wins, and that is expected. That's what we expect to see. The neural network has the advantage of having the full fitting power of the network architecture. So when you have large amounts of data, one should always look to use the tools that one has. But I suppose the danger is that if you want to use a method like fine-tuning in an active learning setup, then you have many, many, many times to fine-tune the network. You have to spend the resources on fine-tuning many times, which means you have to have implemented your entire search strategy on the GPU, and you need to have access to a GPU for the whole thing, which could be quite wasteful. Comparing to our GPR delta model, which isn't particularly fantastic for large data sets, but otherwise is really quite cheap and efficient from an active learning standpoint. So our resultant methodology ends up looking something a little bit like this, where we have a way of exploring our potential, which I haven't explained, but it's global optimization of sorts. A way of exploring could be molecular dynamics, whatever you like. In our case, global optimization. And then DFT, retraining a model. So in a delta model here, which with active learning is very cheap. And then repeating this process in order to build a combined model that hopefully has the knowledge to solve the particular problem that you're interested in. So again, heavily exploiting the information encoded within the potential by spending some time exploring it, spending some time understanding what it currently thinks is good, to be able to then correct that if required. So let's look back to one of these examples that I mentioned earlier, which is this C3 by 5 root 3 reconstruction on the silver oxide surface. It's this large phase in the middle here. CHGNet thinks it looks like this, which doesn't line up at all. It looks reasonable. It represents an understanding of the basic chemistry of the elements involved, but perhaps misses some phenomenological surface information that we wish to encode with our delta model. So what we do is we gather our data in this same method that I outlined above, and let's omit the solution to make it a little bit harder for us, because it wouldn't be fun if it was easy. And we'll build something, we'll build a model out of this, and we'll see if it is able to solve the problem, if gathering data in this way indeed makes some degree of sense. So we start with this, and we compare the energies of the DFT solution and the CHGNet solution. We compare their energies in the delta model as a function of the amount of training data we've applied. And we can see that within basically 100 structures obtained in this manner, we've already flipped the energy ordering very convincingly from a beginning of this CHGNet structure being 0.46 EV beta to the DFT structure being 0.66 EV beta. So we're able to correct the behavior of CHGNet with a pretty small amount of data, and the resultant model knows well that this structure here with the six-membered triangle is indeed the correct solution. But seeing as we were talking about extrapolation, we don't really have to stop there. And you can see that this is more commensurate with this phase here with the triangles. I don't know how well you can see it. I should have made the STM a little bigger, but we can go a little further, assuming my clicker works. And we can say, right, let's take that same data set that we gathered in this way for the smaller unit cell and see if the resulting model has actually managed to learn anything about larger cells. So we'll go up to the P4x5 root 3, which is a slightly wider version of the unit cell from the previous example. And this is the solution indicated in CHGNet, which one can see isn't very reminiscent of this STM solution up here, which has these hollow dark spots, which are nowhere near identifiable here. And then it has these very bright large triangles and smaller triangles, which there's no evidence of them here. So we're very convinced that CHGNet has once again made some mistake here. And by spending some time doing that, by spending some time training our model again on the previous data, we see once again that our resultant model has learned the difference and now correctly predicts this structure to be the best. But, assuming my clicker works, these phases actually exist together, which you might have noticed from this STM. You can see this is the P4x5 root 3 in the STM, and this is the C3x5 root 3. They actually exist together. And this isn't just some kinetic feature of the formation. In fact, these are mobile, these P4x5 root 3 phases. So there's something happening, something energetic happening here, which traditionally with DFT, we probably wouldn't be able to solve given the size of the problem. But let's put our potential to the test and see what's happening at the interface between these two phases by comparing these two examples. One where we have two 4x5 root 3 phases next to each other, and one where we split them apart. And when we do this and relax the structures, which hopefully my GIFs will show here, you can see that we're able to relax those really quite easily and identify that there's an energy difference corresponding to a negative interface energy. So actually, interfaces between the two phases make the structure more stable. And because I don't have much time left, I'll jump straight onto this. Are we at the point where we can model something which is experimentally relevant? Can we model the distance between two of these P4x5 root 3 stripes? Well, it's 8 unit cells and thousands of atoms if you need to go to the correct depth. Can we do that? Can we relax using this potential? Yes, we can. And we see exactly the same behavior where we see this strain being compensated for by rotation in the 6-membered triangles here. And as I say, the most difficult part was actually making the GIF because I'm not very good at that. So overall, what have we learned from this? Well, universal potentials have loads of information in them, and they're going to keep getting better. People are going to keep spending more and more resources finding better and better data sets. They're never going to stop being important, but we're never going to know whether we can trust them for a given system. And this is a really effective and cheap way to make sure that you have a little bit more faith whenever you're applying your potential to a given situation. And the GPR delta model is certainly one way that one can do that. But delta models in general, assuming you have good fitting power on small data sets, are really effective ways of answering this problem. And so with that, I'd like to thank my funding bodies and my group and invite any questions if you have them.
Thank you very much for the talk. There are questions. There's one over there first.
Yeah, thank you for the presentation. I have a question about how do you train the charge net, and particularly about so you can retrain the whole model or you can retrain the final layer. So my question is, when you compare it versus fine-tuning the original model as it is developed and your approach, is it like comparable? And in both cases, whether you're using just retraining the whole or just the final layer?
So we froze some layers when we did the fine tuning. This was some time ago before there was well-established routines for how to correctly fine tune things, assuming that those things even exist formally now. But really, we spent quite a lot of time on trying to find. Let me see if I can go back to that slide. I'm trying to find the best way to fine tune, and effectively a low learning rate with mainly the whole network unfrozen was the way that we found gave us the most reasonable results without completely destroying the behavior of the potential. It was very easy with small amounts of data to absolutely trash the potential. So in these kind of regimes where you have small data, especially if your learning rate is not minuscule, then you can really just destroy the behavior of the potential entirely with small amounts of data. And there are more strategies now where MACE is multi-head fine-tuning, where you attempt to maintain some of the performance of the original potential by contrasting it to some of the original data. But all of these things increase the cost, again, which makes, as far as active learning is concerned, it makes it less attractive as a prospect.
There's another question at the front here.
Hello, great talk. So in your GP, what are you taking as your features?
So the features are local features in this example, but we've also used global features. So it's in this case, it's SOAP descriptor. So it's a relatively simple descriptor. One could use a global descriptor. And in fact, a colleague of mine has just published a paper on using the intrinsic features of the network as the descriptor for this model. To be honest, it seems as though, at least for these relatively simple examples, that it doesn't matter too much. But for systems where you're trying to model something like charge transfer over long molecules or over large clusters, perhaps it matters a lot more what your descriptor is. We're seeing some evidence of that at the moment.
Yeah, great talk. Thank you. So the reason you're using GP for the delta learning is to get the uncertainty. Is that the main reason?
It actually isn't. We could certainly use the uncertainty for part of the active learning, which I think we are doing at the moment. But specifically for training the delta, no. It's just because it's quite cheap and relatively accurate for small data sets.
But there is no end to this, right? So as the data set keeps increasing, and we can expect it would. Are you worried about the scalability of the GP approach?
Oh yeah, I certainly am. That's why my recommendation, I think, would be to, once you have accumulated a sufficient amount of data with this active learning strategy, to consider encoding that data in one fine-tuning step instead of doing 100 different fine-tuning steps in a long, protracted active learning technique. So I think this is certainly best seen as a way of gathering the appropriate data for fixing your model.
Over there.
Thanks. At the beginning, you clarified that you focus on structure optimization and relaxation, which is already very meritory. But I'm curious about the implications for dynamics. So if you wanted to look at processes like self-assembly or so on, of course, you could also do the delta learning for forces, virial. Have you considered this?
Yes. So not in the slides that I presented here, but I have looked at using these models both with data obtained from dynamics and in order to, for example, predict dynamic properties or things like transition states, and it certainly can work in that case as well. So yes, I mean, I think yes is the answer.
Okay, I see no further questions, so let's thank our speaker again.
Thank you.